Well, hello. Today we're going to get started with a discussion of Chapter 1 entitled Matter, Energy, and Measurement. This first lecture is going to be broken into two different parts. The first part on matter and energy, and the second one on measurement. Why study chemistry? Well, chemistry is in the world around us. That's the cheesy answer. But chemistry is the study of matter, its properties, and the changes that it undergoes. One of the reasons why we study chemistry is because the fundamental concepts of chemistry can be applied to all aspects of life. Chemistry is the research that is behind new pharmaceutical products. Chemistry is the development of plastics for food storage, protective helmets, and DVDs. Chemistry is the development of agricultural products, things like weed killers and fertilizers. Now, as with all things, there are the positives, but we have to also consider the detriments for those same three industries that chemistry has influenced. We see that agricultural products, well, sometimes when they get into the soil, sometimes when they get into the water supply, maybe they're not so good for us. As far as those plastics are concerned, sometimes disposing of said plastics can be quite problematic. And as far as pharmaceuticals, all I need to say is if you or your loved ones have tried Somniflex and are experiencing bad stuff, then please call 1-800 Somniflex has messed me up. If chemistry is the study of matter, then I guess we need to get an understanding as to what matter is. Matter is the physical material that makes up the universe. Matter is anything that takes up space and has mass. By taking up space, we say that it occupies a volume. A property is any characteristic that allows us to recognize a particular type of matter and to distinguish it from other types of matter. Now, a discussion of matter is going to involve discussions of elements and compounds and atoms and molecules. But first, we must evaluate the methods of classification, how we can differentiate matter from other samples of matter. In two ways in which we're going to discuss this classification is through the idea of the state of matter and through the composition of matter. Matter can be classified by state, and the three common states of matter are the solid, the liquid, and the gas. These are commonly called the three states of matter. Some of you may be familiar with a fourth state of matter known as the plasma. But if you look up the definition for plasma, it's likely going to say a highly excited form of a gas that under certain conditions, blah, 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 blah. So for now, we're going to treat a plasma as if it is indeed a gas. So once again, the three states of matter, the solid, the liquid, and the gas. In this image, we see water in the three states. Water in the solid state is ice. Water in the liquid state is, well, water. And water in its gaseous state is water vapor. And we can describe those properties on both the macroscopic and the microscopic level. In other words, on the very, very small level and the really, really large observable level. So there are three ways that we're going to compare and contrast those three states of matter. In the proximity of the particles, in other words, how closely packed the particles are with respect to one another, the energy that these particles possess, and we'll have a discussion of energy a little bit later on, and the size and shape of the matter, physically, how that matter presents itself. So in the case of the proximity, matter in the solid phase or in the solid state is made up of tiny little particles, whether they be atoms or molecules, in direct contact with each other. In the liquid phase, those same particles are spread out just a little more. They're not in direct contact, but they're in what we call intermittent contact. They're touching each other every once in a while. They're bumping into each other without being in direct contact at all times. And lastly, in the gas phase, these particles are really far apart from one another. In terms of the energetics of the particles, how much energy they possess. Particles in the solid tend to have a very small amount of thermal energy. That essentially means that they don't move very fast, very rapidly. Particles in a liquid have a little more or a medium amount of thermal energy. And particles in a gas have a large amount of thermal energy. That means that they travel really, really, really fast. Lastly, the concept of size and shape. A solid has a fixed volume as well as a fixed shape. Your textbook is shaped like a textbook, and it takes up about the same amount of space as a textbook. If you cut it in half, you have two halves of a textbook that still take up the same amount of space and still occupy the same shape. Well, two halves making up that same shape. But solids are not very compressible. You can't compress them into a smaller volume. A liquid, on the other hand, while it does have a fixed volume, it does not have a fixed shape. You cannot take 20 ounces worth of soda and place them into a 12-ounce can, because 12 ounces is all that can will hold. You can take 12 ounces of soda and put it in a 20-ounce bottle with room to spare. Wherever that 12 ounces of soda is, it's going to take up 12 ounces worth of space. But it's going to be shaped like its container. If I take those 12 ounces of soda from a can and I pour it into a glass, then it's going to be shaped like the glass. If I pour it into my stomach, it's going to be shaped like my stomach. If I pour it onto the floor, it's going to spread out and be shaped like the floor. But it's still going to take up the same amount of space. It's just going to occupy a different shape. Gases do not have a fixed shape, nor do they have a fixed volume. Gases spread out to fill up their container, and they take the shape of the container that they're in. Whenever I teach this class face-to-face, I often recount a tale from the University of Southern Mississippi of a former research advisor of mine, and a game that he used to play called Molecules. Trust me, it loses something in an online translation. But if you ever see me, if you're ever out and about and you physically see me, feel free to ask me about the game of Molecules. Further classification of matter can be done based on the composition or the makeup of the sample of matter itself. Matter can be made up of elements, of compounds, or of mixtures. And after this discussion, we will likely easily be able to differentiate between an element, a compound, and the two types of mixtures. Now, there are mixtures and there are pure substances. A substance is a material that has distinct properties and a composition that does not vary from sample to sample. There are two types of pure substances. There are elements and there are compounds. An element is a pure substance which cannot be broken down into simpler substances by normal, ordinary means. For example, if I had a brick of gold and I were to cut that brick of gold in half, and I were to cut a piece of that in half, and then cut 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 that in half. Each step along the way, fundamentally speaking, I still have gold. Gold is one of the elements that exists in the universe. A compound is a pure substance which can be broken down into simpler substances because it's made up of more than one element. If I were to take sugar, sugar, sprinkle on your cornflakes to make them taste like Frosted Flakes, even though they're not really going to taste like Frosted Flakes because it's not like baked in there. Well, sugar, commonly known as sucrose, is made up of carbon and hydrogen and oxygen. So sucrose is a compound that can be broken down into carbon, hydrogen, and oxygen. And those three substances are all elements. So how do we describe matter on the microscopic level? Well, when I take that brick of gold and I cut it in half, 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 I'm going to get down to the tiniest piece of gold that can no longer be cut in half anymore. And that piece of gold is called an atom. Atoms are the basic building blocks of matter. Each element is made up of a unique kind of atom. And in chapter 2, we're going to discuss at length the identity and the makeup of an atom. But if gold is made up of a specific type of atoms, and oxygen is made up of a specific type of atoms, and helium and hydrogen and nitrogen and carbon are made up of specific types of atoms, a sample of matter that is simply that type of atom is known as an element. A compound is made when we take atoms from two or more different elements. If you take two atoms of hydrogen and one atom of oxygen, they combine to form a compound known as water. Now, the basic fundamental particle of a compound is a molecule. There are currently 118 named elements. Of those, we have things like hydrogen, oxygen, carbon, nitrogen. I could keep going, but there are 118 of them, so I'll stop right there. Our galaxy is made up primarily of two elements. Hydrogen constitutes 74% of the mass in the Milky Way galaxy. Helium constitutes 24%. The rest of it, the rest of everything that we know in our galaxy, is the 2% of all of the other elements that we know. Only 5 elements make up 90% of the Earth's crust by mass. From the figure you can see that silicon, oxygen, calcium, iron, and aluminum make up 90+% of the Earth's crust. And by the Earth's crust, I'm including the atmosphere as well as the oceans. The human body is made up primarily of carbon, hydrogen, and oxygen. Now you throw in some nitrogen, some phosphorus, some sulfur, and then we're talking about a considerable percentage of the human body. You'll notice that oxygen is present in both the human body in great amounts, as well as the Earth's crust in great amounts. Oxygen is pretty important, but we'll talk about that a little later. Here we see a listing of just a sample of a few common elements, as well as what we call their chemical symbols. Symbols are 1 or 2 letter designations that refer to a given element. If the designation involves 2 letters, the first letter is always capitalized. The second letter is never capitalized. If it's simply 1 letter, then that letter is capitalized. So we see things like carbon and hydrogen and oxygen. with the chemical symbols of C, H, and O, respectively. Now, in some instances, we may find that the chemical symbol doesn't necessarily correspond to the English names of the atoms. For example, in the right-hand columns, you can see copper, iron, and lead. Well, the chemical symbol for copper is Cu. Well, last time I checked, there is no U in the word copper. But if you know that that designation comes from the Latin word cuprum, if you know that the designation Fe comes from the Latin word ferrum, you know that the Latin word for lead, plumbum, gives rise to the Tb, that is the chemical symbol for lead. It should be noted that the Romans, in constructing their water systems, used lead pipes. It's where we derive the word plumbing. But once again, we will talk more about the elements, their symbols, and their uses in subsequent chapters. Compounds are samples of matter that have a definite or a fixed composition. Ultimately, what that means is, while we do have more than one element represented, that they present themselves in a very fixed manner in terms of the number of atoms in a sample. If we take 2 atoms of hydrogen and 1 atom of oxygen, they will combine to form water. If we instead take 2 atoms of hydrogen and 2 atoms of oxygen, they will combine in order to form hydrogen peroxide. Those 2 substances should not be confused with one another. Another example, if we take 1 atom of carbon and 1 atom of oxygen, they will combine to form carbon monoxide, a toxic choking gas. If we take 1 atom of carbon and 2 atoms of oxygen, then instead we will see the formation of carbon dioxide, a gas that is instrumental in our respiration in terms of exhaling, and also instrumental in photosynthesis, the way in which plants metabolize energy. Now, while pure substances have their own identity, a mixture, being a combination of 2 or more pure substances, exhibits the properties of those substances that make them up. And a mixture can vary in composition, or it can have the same composition throughout. I'll give you 2 examples. In the first example, I want you to imagine a glass of water and a tablespoon of sugar. I want you to stir it up, stir it up, stir it up, stir it up, stir it up until it is completely dissolved. That type of mixture is what we call a homogeneous mixture. That's also known as a solution. A homogeneous mixture has the same composition throughout the sample. That means that in the first sip of sugary water that I taste, it's going to have the same amount of sugar and water as in the last sip. The air that we breathe is a homogeneous mixture of gases. The air that we breathe is made up of nitrogen and oxygen and argon and a series of other trace gases. But every single inhale of gas that we take is made up of the same nitrogen and oxygen and argon in the same amounts. Air is about 79% nitrogen, about 20% oxygen, and 1% everything else. Now, the second type of mixture is known as a heterogeneous mixture. A heterogeneous mixture can vary in composition throughout a sample. If you would imagine a bucket that is filled with salt and sugar and sand and pepper. And I want you to shake it up, 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 shake it up. I want you to take a plastic scoop, and I want you to scoop out 1 scoop's worth of that mixture. And I want you to take another scoop of the exact same size and scoop out another scoop of that mixture. It's not necessarily going to be true. In fact, it's not likely going to be true that in each scoop you're going to get the same amount of salt, sugar, pepper, and sand. That type of mixture can vary in concentration. There can be a whole bunch of sand at the bottom. There can be a whole bunch of sugar at the top. All right. That type of mixture is known as a heterogeneous mixture. Now that we've talked about the classification of matter into pure substances, which are elements and compounds, and mixtures, which can be homogeneous or heterogeneous, now we're going to talk about the properties of matter. Shortest slide ever. There are 2 types of properties that we're going to discuss. There are physical properties and chemical properties. Physical properties are those properties of matter that can be observed without changing the substance in question into another substance. In other words, we do not see a change in chemical composition when we are observing physical properties. Some examples include color and odor. If I look at a bottle of milk, I will notice that the milk is white. By observing that the milk is white, it does not change the milk into something else. If I smell the milk, it does not change the milk into another substance. So physical properties can be observed without changing the substance into another substance. Contrary, chemical properties can only be observed when a substance is changed into another substance. One example of a chemical property is flammability. For example, if I were to take a glass of water and drop a match into it, it would not change because water is not flammable. If I were to take a glass of ethanol and drop a match into it, well, then we would see quite the spectacle, because one chemical property of ethanol is that it is indeed flammable. Things like acetone, paint thinner, flammability is one example of a chemical property. And other examples of chemical reactivity could be considered as chemical properties. If we take baking soda, a chemical property of baking soda is it reacts with vinegar or acetic acid in order to form a volcano. Okay, everybody's done the baking soda volcano thing. Baking soda reacts with vinegar in order to produce a new substance. At the end of the day, the substance that is produced is no longer vinegar, nor is it baking soda. What is the new substance? Well, I'm sure that we'll talk about that at some point in the future as well. In the same way that we have physical properties and chemical properties, we also have chemical changes and physical changes. Physical changes are changes in matter that do not result in a change in the composition of the sample of matter. Examples of physical changes most prominently are those changes of state. If I take liquid water and I freeze it, that is a physical change. It's a change in the observation of the matter. The description of matter would be different, but the substance itself is still water. It is still chemically H2O, still 2 atoms of hydrogen, 1 atom of oxygen. If it doesn't form a new substance, then the change is a physical change. If I take a piece of paper and I rip it in half, that is a physical change. If I take a glass of water and I boil it, I now have water vapor, which is still water. That is still considered a physical change. A chemical change, on the other hand, will result in new substances being formed. If I take baking soda and vinegar and I mix them together, then I'm going to form new substances. I'm going to form sodium acetate. I'm going to form carbon dioxide. I'm going to form water. A common way of differentiating between physical changes and chemical changes may not be the most correct way, but many times it will suffice. If the change can be easily undone, oftentimes it is classified as a physical change. I'll give you an example. The boiling of water. Can you unboil water? Well, sure. If you take water vapor and you cool it down, then you can condense it back into the liquid state. The freezing of water. Can you take solid water and make it liquid water again? Well, yeah, you just heat it up. All right. These changes can be easily undone. If I take a piece of paper and I rip it in half, can I undo that? Yeah, just stick it back together and put the two pieces of paper back together. All right. But for chemical changes, it's not so easy. I want you to think about the cooking of pancakes. All right. You stir up all these things. You take some eggs, you take some flour, you take some this, you take some that, and you make the batter. And then you apply heat to it. You cook the pancakes. Well, can you uncook a pancake? Can you take that pancake and revert it back into the eggs and the flour and the water? No, because a chemical change has taken place in the formation of tasty pancakes. How about scrambled eggs? All right. You might think that it's breakfast time as I'm preparing this lecture. But when you scramble eggs, the heat transforms the proteins into a new form. So a chemical change is taking place. You can't unscramble an egg. So these are examples of chemical changes. Once again, looking at the three states of water can allow us to observe the physical changes or the concept of a physical change. And in the case of a chemical change, also known as a chemical reaction, we'll see that the substances in question are converted into totally new substances. Here we see an example of a copper penny that is reacting with nitric acid. At the end of the day, we see a new substance known as copper nitrate and a gas known as nitrogen dioxide. Now, our discussion of energy is going to be quite brief. I find that a discussion of energy is more appropriate in chapter 5. So when we get to chapter 5, we'll talk about energy in more detail. But as it stands, energy is the capacity or the ability to transfer heat or do work. Work is the form in which energy is transferred when a force is exerted on an object that causes a displacement of that object. In other words, it causes that object to move. Heat is the energy transfer, or rather the form of energy transfer that causes a change in temperature. Force, which is directly related to the concept of energy, is any type of push or pull on an object. And finally, the two fundamental forms of energy are kinetic energy and potential energy. Kinetic energy, which we commonly refer to as the energy of motion, and potential energy, which is energy of position. If energy is the ability or capacity to do work, Then ultimately, we're going to explore the role of energy in chemical reactions. Some substances release energy when they react. An example of this is a fuel. The fuel that an energy produces is a result of the potential energy that is stored inside the arrangement of the atoms. That energy is released when the glue that holds atoms together is formed, and it's consumed when that glue essentially gets broken. And again, we'll talk more about the nature of kinetic energy and potential energy and their role in chemical reactions at a later date. So this basically wraps up the first section of chapter 1 in your textbook. I think these are sections 1.1 through 1.4. Our next lecture will be dedicated totally and solely to measurement. Thank you and have a great day.